Hi everyone! So in today's video we're going to be talking about some applications of what we've learned in calculus so far. So basically thinking about how rates of change relate to some kind of real world situations. And this is an idea that we're going to kind of keep working with throughout the quarter, but I just wanted to introduce it early enough so that later in the quarter, as we have different types of examples of functions and we learn more and more derivative rules, we can also do these application problems and get a sense of how some of this stuff is used. So the general thing, so we're still going to be kind of in section 3.1 in terms of the types of derivatives that we're taking, but I guess I'm just kind of making this section name up because it's not really its own section, but we're just kind of looking at some early applications of derivatives. Okay, so the most important thing to know about how derivatives kind of relate to situations is that they measure the rate of change. So if f of x, and maybe actually let me write f of t, because all the examples we're going to be looking at today are going to be related to time. So I'll just say f of t. So if f of t is a function that basically gives a quantity, so that quantity could be a number of different things. It could be like a population, it could be a distance, it could be, what was the other one I just thought of? It could be like temperature. That's what I mean. When I say a quantity, I just mean, some amount of something as a function of time. Then its derivative function, f prime of t, gives you the rate of change of that quantity. As a function of time. So I want to do one initial example that is kind of a more just like straightforward, simple example, and then we'll be getting a little bit more into examples dealing with position functions and velocity and acceleration, because that's a very kind of classic application of derivatives. So for example, let's say that you have a population of bacteria. So the number of bacteria in a sample after t hours is given by, what did I say? F of t is equal to 1.3 e to the t. So as I mentioned, exponential functions are used a lot to model growth of different kinds of populations and things like that. So the question here is we want to find at what rate is the population growing after 10 hours. So how would we answer this? Basically, we're just looking for the derivative and then we're going to plug in 10, right? Because the derivative will tell us kind of like what is the rate of change at every different t value. And then to figure out what is the rate of change at this specific t value, that's where we have to plug in 10. So luckily, this is a pretty easy derivative to take because remember that the derivative of e to the x or e to the t in this case is just e to the t. And then what does this 1.3 do? Well, that's a constant multiple. So we're multiplying by 1.3, and so that's just going to come along for the ride. So the derivative is actually the same as the original function. And that's actually what's always going to happen. If you have like a number times e to the t or a number times e to the x, it's just going to be its own derivative because of the fact that e to the x is its own derivative, and then you're just multiplying by a constant that just kind of comes along. So if we want to know specifically what's going on at 10, we would plug in 10 for t. And so 1.3 times e to the 10. So if you plug this into a calculator, you'll find that this is approximately equal to 28,634. And so let's think about what the units would be. Well, the units of the original problem are bacteria, number of bacteria. And here we're looking for the rate of change of the bacteria, so it should be bacteria per hour. Okay, so let's look at an example now relating position and velocity and acceleration. So I want to jump straight into an example, and then we'll kind of use it as a way to write down some general stuff. So let me just pull this up here. So maybe let me write at the top here. So now we're going to be talking about position, velocity, and acceleration. So let's say that we have a function, and it's a function that is, I know there's multiple functions here, but we're going to be focusing on this function that's graphed in red. So I'll just write it in red. So let's say that the height of a ball after t seconds, and maybe let me write this as a full sentence then. So the height of a ball thrown in the air is given by h of t is equal to negative 16 t squared plus 64, actually, sorry, I changed it for our sake. So it was actually plus 19 t plus 6, where height is measured in feet and time is measured in seconds. So that's the function graphed in red here. So one thing I just want to pause and kind of acknowledge here, because I think it's just like a very easy misconception to have. So if you have a graph like this that is showing the trajectory of a ball or an arrow or something that's kind of thrown into the air, the picture that we're looking at here is not, I mean, I kind of just said it, I missaid it. It's not actually the trajectory of that ball. We're not looking at a map that shows the ball traveling through space. What we're looking at is the horizontal axis is our time. So we're looking at what's the height of the ball as time goes on. So it's basically like if you were to kind of take a snapshot of the height of the ball after each moment and kind of put them all next to each other, that's how you would get this picture. But the ball is not actually kind of arcing through space or through space. It's really just going up and down in this situation. And the reason I'm emphasizing that is that for the sake of this class, when we're talking about position functions, so functions that give a height or a position, we're only going to be talking about motion that is in one direction. Because if we had motion where something was kind of zigzagging back and forth or going through space in a three-dimensional way, we basically would have too many variables to be able to do this calculus class with it, because this is calculus where we're only dealing with one variable. So yeah, we're just thinking about like one direction of motion in this class. So we'll typically be thinking of examples where you have a ball thrown up in the air and then coming straight back down, or, you know, like a particle moving along a line, or we could say like an ant crawling on a stick, something like that, where something is just kind of going in a straight line. Okay, so that's our position function. So let's say that we wanted to find a function, or let's talk about what it would mean to take the derivative of this position function. So if we were to take the derivative of this, we would get, just using the power rule, so we could bring down that 2 and multiply it with negative 16, and we would get negative 32t plus 19. So that's the function that I have graphed in blue. So let's think about what that tells us about this situation. So h prime of t would be the rate of change of the height of the ball. And so rate of change of position in general is something that's called velocity. And so you can think of velocity as being speed, except that usually when we use the word speed, we just use positive numbers. So you wouldn't say I was driving down the road at a speed of negative 30 miles an hour. You would just say I'm driving at a speed of 30. So when we're talking about velocity, we're using it to be able to describe both how quickly something's moving and also whether it's moving forward or backward. So this is what's called the velocity of, in this case, the ball. So it tells us after t seconds, how quickly is this thing moving, and then also the sign of it tells us whether it's moving or forward, or I guess in this case, up or down. And so we'll get to that idea in a second. So I want to just quickly mention what the units are here. So the units are going to be it's kind of similar to what we did in the last example. So we look at the units of the original one. So the original problem, the units were feet. So this one is going to be feet per second, because we're looking at, you know, how many feet has it traveled over a certain period of time. So it's feet over seconds, or feet per second. So we can also call this, and I guess I didn't really leave myself space, so let me move this a teensy bit. So instead of calling this h prime of t, we could also call it v of t for velocity. So we'll get to talking in a moment about what exactly the velocity tells us and kind of seeing where it's positive and negative, but I just want to talk about the one last function. So if we take the derivative again, that's going to give us something called acceleration. So a of t is, there's kind of two ways to think of it. You can either think of it as you're taking the first derivative of velocity, or you can think of it as you're taking the second derivative of position, right? Because when you take the second derivative, it's like you're taking the derivative of the first derivative. So because velocity is the derivative of the height, then you take the derivative again and you get the second derivative. So what would that be in this case? It would be negative 32. So because when we take the derivative of this function, we just have negative 32 times t, so the derivative of t is just 1, so we're just left with negative 32, and then the derivative of 19 is 0. And so that's why on this graph, the acceleration function is just a horizontal line. It's because it's a constant function. It's constant acceleration. Okay, so this is the acceleration of the ball. So what is acceleration? So when you hear the word acceleration, you probably think about speeding up, right? Oh, I put my foot on the gas and I accelerated. And so that's part of it. Acceleration, I mean, if we think about like what's going on here, it's the change in the velocity, right? So it's it can be speeding up, but it can also be slowing down. So acceleration basically talks about how is the velocity changing? Is it becoming more negative? Is it becoming more positive? Things like that, like sort of seeing how the velocity is changing over time. So the units for this are a little bit funny, but if you think about it, it makes sense. So where did this feet per second come from in the last example? Well, it's because in the original function, we had feet and we had time measured in seconds. So we're doing change in output, which is feet, divided by change in input, which is seconds. So we got feet over seconds. So for our new function, well, now we're taking the derivative of v of t. And so our units in v of t are feet per second. And so the units for this one are actually going to be feet per second per second. So I know that seems maybe a little nonsensical, but it's basically just saying, the numerator is the velocity. So it's saying like what's going on with the speed of the original object. And then we're talking about how is that changing as time goes on. And so that's how we end up with this per second thing twice. And so there's a nicer way to write this, which is you usually actually write it as feet per second squared. And I know that seems a little weird, like what does second squared mean? It really just means that you're dividing by seconds twice. It's just kind of a shorthand instead of having to write what I wrote here. Okay, so what is this? Let's talk about what these different functions tell us about our ball and our motion in this case. So as we mentioned, velocity tells you about the speed of your object, but also what direction it's traveling in. So if we look at the original graph, we can see that it's going up during this part, right? And then it's going down, because if we're just kind of thinking about the height over time, we can tell just by looking at that picture that, oh, it's going up and then it's going down. Notice that matches up with where the velocity is positive and then where the velocity is negative. So during the time period that the ball is going up, the velocity is positive. And so again, I'm just going to reiterate this because I think a lot of students kind of get confused about this, and I understand why. We're going to be talking a lot about increasing and decreasing and positive and negative, and I just want to be really clear that whenever I say a function is positive, all I mean by that is that the function lies above the horizontal axis. So for example, this velocity function is going down, right? From left to right, it's going down. But this part of the graph is positive because it lies above the t-axis. So that's what I mean when I say positive. I just mean where does it kind of live on the xy coordinate plane. Whereas on the part of the graph where the ball is traveling downward, then the velocity is negative. Okay, so what are we saying here? We're saying that when v of t is positive, the ball is traveling upward. And when v of t is negative, the ball is traveling downward. And then what's happening when the velocity is equal to 0? Well, then the ball is kind of in a transition point. So it's neither moving upward nor downward. So you can think of that as a turning point. It's kind of like momentarily, like picture throwing a ball up in the air, it just kind of pauses for a second before it comes down. Okay, so hopefully you can see kind of this connection between the velocity and the position, in this case, the height graph. Okay, so what about the acceleration? What does this tell us about our function? So most students, if they had to kind of guess, usually guess, oh, well, if the acceleration is negative, that means that the object is slowing down. But that's actually not the case. Because if you think about it, it doesn't really make sense that if you throw a ball up in the air, it's not going to be slowing down the whole time. It actually is going to get faster and faster as it gets closer and closer to the ground. So this is an example of a function that has a constant acceleration. And actually, in this case, it's the acceleration due to gravity, right? So if you throw a ball up in the air, it's going to come down because it's being counteracted by the force of gravity. And gravity is a force of acceleration, or a force that causes things to accelerate as they get closer and closer to the ground. So what's actually happening here is that during the time period where the ball is traveling upward, it's actually slowing down, right? Because like the acceleration is going in the opposite direction. It's pulling the ball down while the ball is trying to go up. So the ball is actually going to be slowing down while it's going up. However, once the ball has turned around and has started to come down, then it's actually going to start speeding up, right? Because that downward force of gravity is going to pull it down faster and faster. So it turns out that it's not so simple to figure out whether something is speeding up or slowing down as just seeing whether the acceleration is positive or negative. You also have to see, basically you have to see if the acceleration agrees with the direction that the object is traveling. So think of acceleration as being a push in a particular direction. So in this case, we have two directions, right? We have up and we have down. And the acceleration, because it's negative, is in a downward direction. So during the time periods that the ball is going up, that downward acceleration is causing it to slow down. But as soon as the ball is going down, now both the acceleration and the ball are kind of going in the same direction, and so it causes it to speed up. And so the perhaps like the easiest way to think about this is that to actually look at the velocity and the acceleration together. So remember, the velocity tells you about whether something is going in the forward or backward direction. So if something is, if the velocity and the acceleration are both positive, then that will tell you that the object will speed up because the object is moving forward and its acceleration is in the forward direction. If they're both negative, then that will mean that the object is speeding up as well because it's moving in the backward direction and the acceleration is also going in the backward direction. So that's like what's going on here in the second half of the graph. It's going downward, its velocity is negative, acceleration is also negative. But if the acceleration and the velocity are opposites, so like in this part of the graph, where the velocity is positive but the acceleration is negative, then it actually causes things to slow down. So let me write that. In this case, basically what we can say is that when the velocity is positive, but the acceleration is negative, so that's kind of on the first part of the ball's travel, the ball is slowing down because the acceleration is pulling it in the opposite direction as the direction that's traveling. And then in the second part, the second half, when the velocity is negative and the acceleration is negative, the ball is speeding up because the directions agree. Okay, so I want to just kind of summarize what we said in general, and then we'll do one more example of looking at, again, the position, acceleration, velocity, kind of seeing how those all relate to each other. So this page is just going to be kind of a general summary of what do velocity and acceleration tell you. So first of all, just kind of most general thing that we saw on the last page is that if S of t gives the position of an object as a function of time, then if you take the first derivative of the position, you get the velocity. And that is going to give the velocity of the object as a function of time. And then if you take the derivative again, so if you do s double prime of t or v prime of t, you get the acceleration function. So again, just kind of most general idea about this is that the velocity is the change in position, right? And then the acceleration is the change in velocity. So it's about speeding up or slowing down. So what else can we say here? So same kind of stuff we were saying on the last page, but I just want to summarize it. So in general, if the velocity is positive, the object is moving in the positive direction, however that has been defined. So in our last example, we would count up as being the positive direction, but our next example, it will just be kind of forward and backward. If the velocity is negative, the object is moving in the negative direction. And then we also said that if the velocity equals 0, the object is not moving. And that doesn't mean that it's like really kind of stopped. It's just sort of like usually it's just like a moment of motionlessness between, like, as it's changing direction. So maybe I'll say that it's usually thought of as like a turning point between going forward and backward, or sort of turning point. It's been a long day. And then the last thing that I want to write here is about acceleration. So basically, it's what we just said on the last page. So if both the acceleration and velocity are positive, or both the acceleration and the velocity are negative, the object is speeding up. Another analogy I like to give for this is think you're like walking or running or biking or something, and there's some wind, and the wind is kind of pushing you. So if the wind is in the same direction that you're traveling, it's gonna help you, right? It's gonna speed you up. So that would be this situation. Regardless of which direction you're traveling, if the wind direction agrees with you, then you're going to be helped by that wind. On the other hand, regardless of which direction you're going, if the wind is going the opposite direction, so that would be either the acceleration is positive and the velocity is negative, or the acceleration is negative and the velocity is positive. So now that's like the situation where you're biking into some headwind, right? And it's like really slowing you down. And so that's the kind of situation where things would be slowing down. Okay, so I want to do one more example using these ideas. So let's say that we have a, what did I call it? We have a bug crawling on the stick. So a bug is crawling on a stick. Its position in inches after t minutes is going to be given by s of t is equal to t cubed minus 4t squared plus 4t. Oh, and then this is restricted to, we're just looking at a period of 3 minutes. So like that. So we're going to do a few things here. So first thing we want to do is we're actually not going to sketch the original function. And this is really kind of the power of derivatives, is that without, in the last example, we were kind of comparing side by side the position graph, and we could kind of use that to support what we were saying about the velocity. But you really don't need to do that. So if you know the velocity and the acceleration function, just by looking at those, you'll be able to understand things about how this motion is happening. And the nice thing is that when you take the derivative of a polynomial, like our position function is here, it becomes a simpler function, right? So the velocity and acceleration functions are both going to be simpler functions to work with. And so just by graphing those two, that will tell us like most of what we would need to know about this bug. Okay, so first thing we want to do, let's start by finding the velocity function, and we're going to graph it. So how would we do that? We would take the derivative of our position function, and we get 3t squared minus 8t plus 4. So just using the power rule. So how would we go about graphing this? Well, we know that it's going to be a parabola, right? It's a quadratic function. So let's try to find the t-intercepts and the y-intercept, and that should be enough information for our purposes. So really all we're going to need to we don't need to know like too many specifics of exactly where every point is. We just need to know where it's positive and where it's negative. So that information alone will be enough for us. So to find the t-intercepts, so this is some algebra review. We're going to set our function equal to 0, right? Because if you're looking for the t-intercepts or the x-intercepts, you're looking for where are the y values 0. So we set the whole function equal to 0. So how does this factor? Well, we know that we were going to need, so my general recommendation for factoring is usually just going to be trial and error. I think trial and error can definitely get you a long way. So what I mean by trial and error is basically we can tell that if we're supposed to get a 3 here, 3t squared, that tells us that we need to have a 3t and a t, right? Well, that's really the only combination of integer coefficients that could give us 3t squared. And then we're supposed to have a plus 4 here. And so we really don't have that many options. Really, our only options are so what do I mean by that? So to get this 4, these two numbers here have to multiply to give us 4, right? So either it's going to be like 1 and 4, or 2 and 2, or -1 and -4, or -1 and -2. Those are really our only choices. And because this number is negative, that's a good hint that we're going to want to go with one of the negative choices. So I happen to know that this is the right factorization, but you could just do trial and error. It's not going to take you that many tries. If you choose the wrong one, then it's going to be the other one. So this is the way it factors. And so then we can set each of these factors equal to 0. And we'll find in this case that 3t is equal to 2. So t is going to be equal to 2/3. And then this one we get t is equal to 2. And so that tells us that our graph is going to go through the point 2/3. So let's see, somewhere around this point here. And then also go through at 2. And then how do you find the y-intercept? Well, you just plug in 0 for t. And what happens when you plug in 0 to a quadratic equation or function is that you just get left over with the constant. So we get 4. So that tells us that our graph is going to look something like this. And if you wanted to figure out exactly what, like where the vertex was, one way that you could do it is you could find the point halfway between the two x-intercepts, or two t-intercepts in this case. And then just take that t coordinate and plug it in to find the y coordinate. And actually, let me erase, because we don't want the part that's before t equals 0. So something like that. Like I said, it doesn't really matter that much that we're exactly precise on this. Okay, so let's now find the acceleration function and graph it. Graph it is not one word. Sorry, I'm struggling to find my eraser button. There we go. Okay, so our acceleration is going to be the first derivative of the velocity, right? So we just want to take the derivative of that velocity function. So a of t is going to be the derivative of the velocity, which is equal to 6t minus 8. So what does that look like? It is a line that has a y-intercept of -8 and a slope of 6. So we can just count up 1, 2, 3, 4, 5, 6 over 1. 1, 2, 3, 4, 5, 6 over 1, and connect our points to get a rough idea of our graph. Something like that. Okay, so the next thing we want to answer is we want to figure out when is this bug moving forward and when is it moving backward. So when is the bug crawling forward, and when is it crawling backward? So what do we want to look at here? We just want to look at the velocity and figure out when is the velocity positive and when is the velocity negative, right? Because when the velocity is positive, that tells us that the bug is crawling forward. When the velocity is negative, that tells us the bug is crawling backward. So looking at our velocity graph, we can see that it is positive from the start, so 0 seconds, up until 2/3. So maybe let me put that point on here. This was t is equal to 2/3. And this is 2. So that tells us that the bug is crawling forward. And I'm going to use interval notation here because, and I guess it doesn't really matter whether you put a bracket or a parenthesis at 0. Technically, I mean, you'll see actually probably different things depending where you look. I'm just going to put a bracket. But what is important is when we get to 2/3, we should put a parenthesis because at 2/3, that's when the velocity is actually equal to 0. And so we don't want to include that. It's like up to 2/3, but not including 2/3 is when this thing is moving forward. And then when else is it moving forward? Well, it's moving forward after 2 seconds. So from 2 to 3 seconds. And so if you remember how interval notation works, you can put this U, that means union, and it's just a way of kind of saying you have multiple intervals and including both of them. And so when is it moving backward? It's moving backward when the velocity is negative. And so the velocity is negative from 2/3 up until 2. And again, we're not including those transition points because that's where it's neither moving forward nor backward. Okay, one last question is going to be, when is this thing speeding up? And when is it slowing down? So this is where we need to be a little bit careful. And this, I think this can be kind of a tricky one just to visually be able to understand what's going on in the graph. But we're going to be looking at both the acceleration and the velocity. And we basically want to kind of scan from left to right and determine whether they are either both positive or both negative, or if one's positive and one is negative. So one thing that we're going to need that is not on this graph currently is we're going to want to know what this point is, because that's the point where the acceleration goes from being negative to being positive. And so that point is going to come into play. So how can we find that point? Well, basically the same way that we found the t-intercepts of the velocity, we can just take the acceleration and set it equal to 0. So the t-intercept of this acceleration function is going to be what we would get by setting 0 equal to 6t minus 8. So 8 is equal to 6t. And so that tells us that t is equal to 8 over 6, which is the same as 4 over 3. So I'm just going to put that onto our graph for reference. Maybe I'll put these here so that looks a little clearer what I mean by that. Okay, so let's kind of scan from left to right. So when we're scanning from left to right, as we start out, the velocity is positive, right? And the acceleration is negative. And so we want to kind of go from left to right and then figure out what's the place where something changes. And so they're both like, maybe I'll even draw some lines here. So like they're both positive, right? Or sorry, one's positive, one's negative. One's positive, one's negative. One's positive, one's negative. And then here at 2/3, that's where it changes, right? That's where the velocity becomes negative. So now both the acceleration and the velocity are negative. And so that tells us that it's speeding up. Okay, so let's write down what we have so far. So we know that it's slowing down. I don't know why my color changed. Okay, slowing down. From the starting point up until 2/3, right? That's where it changed. And then from 2/3, and as we move to the right, move to the right, move to the right, they're both negative, right? They're both negative. So that means that the bug is crawling backward and it's also accelerating in the negative direction. And so because they're both negative, it's speeding up. It's speeding up, but it's also going backward, speeding up in the negative direction. And so that continues until 4/3, right? 4/3 is where the acceleration changes sign and becomes positive. So that tells us that it's speeding up from 2/3 until 4/3. And so now if we kind of keep doing this thing of just imagine kind of like sliding from left to right. So starting at 4/3, well, now the velocity is negative and the acceleration is positive. And so that keeps happening, keeps happening, keeps happening. Okay, here is where it changes, right? Because at 2, now the velocity becomes positive. So the bug is slowing down from 4/3 until 2. And then what's going on from 2 forward? Well, from 2 to 3 seconds, the bug is both the velocity and the acceleration are both positive. And so that means now it's going in the forward direction and it's speeding up. So it's speeding up from 2 to 3. And you could put a bracket on this 3 because it's the endpoint. It doesn't really matter. The reason I'm putting a parenthesis is because we don't really know what happens after 3 seconds, whereas 0 was like the starting point, and that's why I put a bracket on that. But I wouldn't worry too much about that part. Again, it's just putting parentheses at these transition points where things are neither speeding up nor slowing down, or neither moving forward nor moving backward. All right, that is it. So thank you all and have a great weekend. And next week we'll get into some more derivative rules. All right, bye-bye.